Okay, so Xavier said that we try to keep things very technical. So basically what I'm going to tell you is that everything that I've told you before about AI is wrong. And to some extent we need to start again from scratch, so that's what I'm doing. So I think we're all familiar with the idea that AI is moving very quickly, it's accelerating, things are happening sooner than many people expected. So this is Lee Sedol. He's one of the world's greatest Go players, and he wasn't expecting to lose to a machine, at least for another 10 years. But he lost, and then all the other human Go champions lost. And then more recently, a version of the same program not only beat AlphaGo, which is the program that beat Lee Sedol, but AlphaZero, the new program, also beat the world's best chess program and the world's best shogi program. So in less than 24 hours, it became world champion in 3 completely different board games. So this might make you a little bit nervous, and so I'll talk about that reaction, which I think is a natural reaction. Let's look at where we are right now, particularly with advances in deep learning, and many AI startups are based around this technology. My student, Andrew Ng, who was chief scientist of Baidu, had this rule of thumb that anything that you can, an ordinary person can do in 1 second is a good candidate for an AI system to do equally well, if not better. And that's not a perfect rule, but actually it works pretty well. So we have learning systems, we have robots that are increasingly capable in the physical world. They are starting to be dexterous, so they can now, pick objects out of bins. They can take things off of conveyor belts and move them around, stick things together. We have Boston Dynamics walking robots, which are both 2-legged and 4-legged, really quite competent at walking and running and climbing stairs. We have flying robots, quadcopters, as well as fixed-wing aircraft that are incredibly agile. We have visual perception that works very well. These are the main areas where deep learning has shown human or superhuman performance: visual perception, speech recognition, machine translation. And we also have, I think, on a completely different line, we now have ways of writing down probability models and doing inference that are universal, meaning that any model that you can write in any language can be written in one of these languages, and they have, with one algorithm, they can answer any question on any model for any evidence. So that type of universality is a very good foundation for future progress, which I think we'll see. And as a consequence of that, I think we're going to have, even if there are no more major breakthroughs, even for decades, we will still see very significant economic impact from rolling out the advances that have already happened. So when you have capable perception and dexterous manipulation, you can put robots, take them out of the factory. You can put them on the roads, as Waymo and Uber and so on are already doing. You can put them in homes. You can put them in fields. They can deal with environments where perception and understanding and manipulation are required. I think another huge area for commercial development is going to be in the area of intelligent assistants. And I don't mean Siri and Alexa. Those are unintelligent assistants. But what they do is they create, you might think of it as a Trojan horse, or an entree into everyone's house. And if you can improve the intelligence of those assistants, then they're worth a lot more money, both to the companies that sell them and to companies that want to use them to sell products to you, and so on. So I think as we start to improve the capability for language understanding in particular, We can have systems that actually read and understand your email, that listen to and understand conversations in the household, that know who you work with, who you're related to, what your projects and activities are, your concerns, and so they can actually be useful assistants in your everyday life. So some of you who are CEOs probably have a personal assistant who's a human, and you probably rely on them to make your life possible. And that capability will, I think, soon be available to everyone for 99 cents a month. And that will be amazing. So another interesting thing about systems that can understand language, even if it's in a very shallow way, is that unlike humans, where once people learn to read, they can read a book, and that's great. They can read another book, and then if you're like my children, that's enough, right? So 2 books, okay, we're done. But the machine will just read everything that the human race has ever written. And that's a game changer. If you think that search engines are worth a lot of money, and they are, maybe 1 trillion euros, a system that can actually read and even to a limited extent understand everything the human race has ever written, everything that's on the web, all the books, all the reports, all the newspapers, all the television programs, everything. That's going to be worth far more than a search engine, because it will be able to integrate that information and answer questions rather than just index it and give you back 42 million documents whenever you ask a question. Now, I do want to say something about the rate of progress in AI. It's not as high as some people in the media would like you to think, and it's not as high as some people pitching startups would like you to think. It's quite common to see this phrase, data is the new oil, right? And it's a very simple meaning, right? That, data is just measured in quantity, right? And the more you have, the better. And whoever has the most wins, right? You see this over and over again. It's something easy that, government ministers can understand. Even government ministers can understand. But well, I wasn't going to say that, if you say so. But it just really isn't true. Quantitative data does not make that much difference. Most learning algorithms actually asymptote, and in fact, some of the newer algorithms that are able to use prior knowledge to learn from new examples actually don't need very much data. Humans need almost no data to learn. We learn new concepts from 1 or 2 examples. And so, the fact that you have 85 million pictures of, a Porsche Carrera doesn't mean that you're going to have a much better recognizer for Porsche Carreras, right? Probably better off having something that actually understands the structure of cars and can learn a Porsche Carrera from 1 or 2 examples. Another possible danger, and this has happened before, so I joined Berkeley in '86. That was right at the height of the last big AI bubble, okay, which was the expert system bubble, and it was a lot like it is now. All the students at Stanford wanted to take the AI course because that was how you were going to get rich. Everyone in the business school wanted to do a startup company with the AI students and the AI faculty. And by 1988, it was all over because the technology was far less capable than the business people thought it was. And we had what was called the AI winter. My AI course in 1990 had about 25 students. Right now, it has, in the fall, when I'm teaching in the fall, it'll be 750. And that's only because that's the size of the room. If we had a bigger room, we could probably have 1,500 students taking the AI course. So interest is very, very high now, but we have to deliver for this interest to stay. Oh, and I did, yeah. So I wrote this slide actually a few days ago, that if there were serious disappointments with autonomous vehicles, particularly because people are spending a huge amount of money developing these vehicles, that if there are some failures, there could be a serious backlash. So I would say the accident that happened with the Uber car, I think it was yesterday or day before yesterday, where someone was killed, a pedestrian was killed, that could be the kind of thing that creates a serious setback, which would then, even though the driving algorithms may be progressing, if they have a setback in that states and countries will not allow them to be experimenting on the road with their vehicles, then the investments may end up failing, even if the technology itself doesn't fail. Okay, so this is all great, and there's much more to do. So we don't yet have anything that looks like human-level AI, because there are still some major breakthroughs that have to happen. We don't have anything that looks like real understanding of language, and if you have a Siri or Alexa, you know that already. So the chatbots don't understand anything that they're talking about. I think one of the biggest problems that we have right now is how to get AI systems to learn to make decisions over long timescales. So let me explain what I mean by that. AlphaGo, which I showed you Lee Sedol, but he was losing to AlphaGo. AlphaGo is a reinforcement learning system, and it plays extremely well, and it uses look-ahead in order to do that. And it looks ahead about 20 or 25, maybe 30 moves sometimes into the future. And that seems like a long way. Now imagine applying the same algorithm to a robot. Right now, modern industrial robot operates around 1,000 hertz. So 1,000 times a second, it can send a new current or voltage to the motors. So looking ahead 20 or 30 steps gets you 20 or 30 milliseconds into the future, right? Which doesn't really help you very much if what you want to do is go on vacation in Hawaii, right? Which is 20 or 30 billion steps into the future. Okay, so methods based on look-ahead and search and all these algorithms for solving Markov decision processes and so on have no chance of scaling up to decision-making in the real world. The reason humans can do it is because we make decisions at multiple levels of abstraction, right? We choose to fly a particular airline. We choose to go to a particular hotel, right? We choose to take a taxi to the airport. And then we take each of those choices and we break it down further, right? We choose to meet the taxi outside and wait for him on the sidewalk, right? We choose to get in the door next to the sidewalk and not the door in the road, right? So we break all these choices down. We operate seamlessly all the time across dozens of different levels of abstraction. And AI systems don't yet know how to do that. They don't know how to learn those levels of abstraction. This is, I think, the biggest obstacle to achieving human-level AI. And if that one is solved, quite possibly the other ones will also be solved. And that will be a big step forward. It's very hard to predict when this is going to occur. Right? These are conceptual breakthroughs that are required. This is not a matter of making machines faster or bigger or collecting more data. None of those things is going to solve these problems. Making machines faster just gives you the wrong answer more quickly. So let me explain what I mean by unpredictable. This is Ernest Rutherford. He was a nuclear physicist, probably the most famous nuclear physicist in the early part of the 20th century. And he gave a speech, kind of like this one, on September 11th, 1933. And he basically said, even though we know that atoms contain a huge amount of energy, it's impossible to ever extract the energy. And he was absolutely convinced of this. And so were many other famous scientists, including Einstein. And this is Leo Szilard, and he read about this speech in the newspaper, in the Times, the next day, and he invented the neutron-induced nuclear chain reaction. So it went from completely impossible, will never happen, at 16 hours later, the problem was basically solved. So I am not in the business of predicting when these breakthroughs are going to happen, but I want people to understand that they can happen at any time. So it seems reasonable to then assume that at some point we will have these breakthroughs, we will solve these problems, and we will have human level and then superhuman AI capabilities. So that could be an amazingly good thing. And I hope that it will be an amazingly good thing. And this is what I'm working on now, to make sure that it's going to be an amazingly good thing. Because, everything that our civilization values comes from our intelligence. So obviously, if we could have more of it, then we could have a better civilization. In fact, this would be a step change in the rate of progress of the human race. And if you just think about it, right, if we just had human-level AI, not sort of superhuman galactic scale intelligence, but just human-level AI, so that we could have intelligent robots that we could ask to do things in the physical world, that we could organize activity on a much larger scale. We could bring the standard of living of everyone on Earth up to the standard of living that we enjoy in Paris, for example. And that would be a 5- or 10-fold increase in the GDP of the world. And you calculate the value of that, it's something like $10,000 trillion. Okay, this is the fruit on the tree that everyone is trying to pick. This is what Google wants, this is what Facebook wants, this is what IBM and Tencent and all these other companies, this is what they want. They want to be the first to pick that fruit off the tree and have a good chunk of that $10,000 trillion value. Okay, so that's the upside. The downside, well, there are many downsides, and you've probably read about them in the newspapers. So using AI to kill people is a very popular thing these days. Having AI systems replace everyone or humans in their jobs, that's another prediction that many economists take very, very seriously. I could give a whole talk about that, but I want to talk about this, the end of the human race. So why is it that people are predicting AI could be the end of the human race? Well, it isn't just Elon Musk and Stephen Hawking, who are not really AI people. Here's a quotation: even if we could keep the machines in a subservient position, for instance, by turning off the power at strategic moments, we should, as a species, feel greatly humbled. All right, does anyone know who said this, who hasn't seen my talk before? So this is Alan Turing, 1951. Right? And actually, Alan Turing, in several speeches and papers, said basically the same thing. Look, AI systems are eventually going to be smarter than us, and then we're toast. Right? He seemed actually completely resigned to this prospect and didn't really propose any kind of solution to it. So you could actually say the same thing about gorillas, because the gorillas, they made something, a few million years ago, they made something that's much smarter than them, namely us, humans. Right? And now they're having a discussion, as you can see. They're having a meeting to say, was this a good idea, right, that we made these humans? And clearly, as you can see from the attitudes, that the answer is no. This was a really bad idea for gorillas to make humans. Right? Effectively, their species only continues to exist to the extent that we permit it. And that's not a future that we want for the human race. Now, if this is the problem, right, that making something smarter than you ends in disaster, right, then we have to stop doing AI. Because that $10,000 trillion prize is going to keep pushing everyone forward. We will get to human-level AI because it has such economic, military, political value. It's going to be very hard to stop us reaching that unless we institute a kind of a global ban on AI research beyond a certain point, which I actually think is really difficult to do. May not be impossible, but I don't think that's a solution to the problem. We actually need to understand why it is that intelligent machines, machines that are more intelligent than us, might pose a problem. So here's another quote: "We had better be quite sure that the purpose put into the machine is the purpose which we really desire." Right, and this is a clearer example of what the problem is, right? That the machine may be given some task to do, some objective to optimize, and in the process of optimizing that objective, it may behave in ways that we are extremely unhappy about. So this quote comes from Norbert Wiener in 1960, and he wrote it because he had just seen the predecessor of AlphaGo, which was Arthur Samuel's checker-playing program in 1959, which learned to play checkers and learned to play much better than Arthur Samuel himself. But the same point occurs over and over and over again in human mythology, right? So King Midas had the same problem. He put into the machine a purpose, namely that everything he touched should turn to gold. And he got exactly the purpose that he asked for, including his food and his drink and his family. They all turned to gold. And then, of course, it was too late. So this actually is a problem that we could try to solve, right? The gorilla problem, I don't think we can solve, right? But this version of the problem, I think we could actually try to solve. But actually, it's more complicated than this. It's not just putting the wrong purpose into the machine. It's also the fact that when you put a purpose into a machine, the machine, if it's sufficiently intelligent, realizes that it will never achieve that purpose if someone switches it off. Right? Even something as simple as fetching the coffee, right? A machine understands that you can't fetch the coffee if you're dead. So now you have a machine that has the wrong purpose put into it, and also it will resist any attempt to turn it off or to interfere with that purpose. And that's a real problem. In fact, this is the plot in the movie 2001, A Space Odyssey. So this is HAL 9000 refusing a command from Dave because HAL has a mission, a purpose, and HAL is afraid that Dave is going to try to interfere with the mission. Now, fortunately, HAL is not super intelligent. Eventually, Dave figures out how to switch HAL off, right? But if HAL had really been super intelligent, then HAL would have switched Dave off. And this is the problem. So how do we make sure this doesn't happen? Well, I thought about this for a while, and I've gradually come to the realization that we kind of made a mistake in the way we think about AI. So the first step in thinking about AI was to think, okay, what does intelligence mean, right? Well, for humans, it means that our actions can be expected to achieve our objectives, right? That's a reasonable definition of intelligence, or rationality, if you like. Okay? And so the natural way to make artificial intelligence is that machines are intelligent if their actions can be expected to achieve their objectives. Okay, perfectly straightforward. And in fact, since they don't have objectives, we have to just put the objectives in, right? And this is what Wiener was complaining about, right? We put the objective into the machine, and now the machine optimizes it. Now, this is not just AI, right? Control theory has cost functions. Economics has utility functions, operations research has reward functions, statistics has loss functions. In all these disciplines, this is how it's done. We specify an objective, and then the machine optimizes it. Okay? And what I'm going to say is that this is a mistake. Right? We do not want machines that are intelligent in this sense because of the King Midas problem. Right? Because of the problem that, if we ask the machine to cure cancer as quickly as possible, it figures out how to induce cancer in every human being on Earth so that it can try different treatments as quickly as possible, because now it has more guinea pigs, right? Et cetera, et cetera. It's easy to think of ways that perfectly ordinary, even benevolent objectives can turn out to be catastrophic for the human race, particularly when the machine is going to stay alive in order to carry out the objective. It's also going to try to acquire more resources to carry out the objective. So it's automatically going to be in conflict with us, and it's going to win. Okay, so what do we want instead? Well, we just have to change the, I forget the French word, anyway, the possessive adjective. So we want machines that are beneficial, which means that their actions achieve our objectives. Not their objectives, not objectives that we put in, but our objectives, even if we don't put them in. Right? And this is a simple change, but in fact, this really does help. And using this change, we can actually make machines that are provably beneficial to us. So, let's see how that works, right? So we want machines that are going to achieve our objectives, so that has to be what they try to do, right? Their only objective is to maximize the realization of human preferences. And when I say human preferences, I don't mean, cheese pizza or sausage pizza. I mean life A or life B, right? Which future life do you want, right? Your whole life and everything that you care about, which would you prefer? Okay? And then the second point is that the robot does actually not know what your preferences are. The robot is explicitly uncertain about your preferences. So this is the real change, right? Rather than specifying the objective, the machine is going to be uncertain about what the objective is. And it's that uncertainty, that humility, that gives us a margin of safety. Now, if the robot is completely uncertain about our preferences, then it's going to be completely useless. It's not going to be harmful, but it's going to be completely useless. Probably it will just do nothing, right? So the robot has to be able to learn information about our preferences, and the source of information about human preferences is actually human behavior. Every time we make a choice, we reveal information about our underlying preferences, okay? So that's the third principle. And I'll explain more about, I have an asterisk there because in fact this is probably the most difficult of the principles to put into practice. So let me illustrate how this approach allows you to switch off a robot. Right, here is the robot in my lab, and there is the off switch. Okay, and just to remind you of what the problem is, right, here is the old-fashioned way of doing it. We give the robot the objective to fetch the coffee. I can't fetch the coffee if I'm dead, therefore I must disable my off switch and kill all the other customers in Starbucks. Right? This is not what we want to happen. Okay, so how do we prevent it? Well, if we have uncertain objectives, the robot can reason in a different way. Right? It says, okay, the human might switch me off, but only if I'm doing something wrong. Okay? Now, the robot doesn't know the true objective. It knows something about the objective. It knows you want coffee, but it doesn't know the other stuff. It doesn't know how much you care about the other customers in Starbucks, and so on. There's lots of other things it doesn't know. It just knows you want to get coffee. So it doesn't know what wrong means, But it knows it doesn't want to do wrong things because its objective, the first principle, its objective is to help you realize your preferences. So the robot should be happy to be switched off, because if it is switched off, that prevents something happening that the robot does not want to happen. Okay? And in fact, you can prove by turning this all into Greek that such a robot is provably beneficial. Okay? That it has a positive incentive to allow itself to be switched off. It doesn't have a positive incentive to switch itself off, which is good. We don't want robots just committing suicide just in case they do something wrong, right? But it has a positive incentive to allow itself to be switched off. And this robot, therefore, basically, it either, it says, is it okay if I do this? And gives you a chance to switch it off. And if you're happy with the action, it will go ahead and do it. And if you're unhappy, you can switch it off, right? And so it's provably beneficial. This is a very simple mathematical theorem, but it's also very general. So this has actually led me to think again about many different kinds of problems in AI, almost all of which are done using fixed objectives. And let me give you one example. This is probably, for many of you who are, if you're working on image data, or text data, same problem, right? The standard way of doing this is you run a machine learning algorithm and you minimize, the squared error, right? And the squared error is basically calculated using the loss matrix. The loss matrix says, what is the cost of misclassifying an object of type A as an object of type B, right? What is the cost of classifying a cat as a dog? Now, pretty much everyone, including, I believe, Google, uses a uniform loss matrix, right? And in fact, if you have a uniform loss matrix, then you don't even worry about the loss matrix, right? It just disappears from your equations. And that's a huge mistake, right? Because then you accidentally classify a human as a gorilla. And you spend billions fixing this very bad public relations disaster. Okay, so this is what happened to Google. And the reason was that they just had the wrong loss matrix, right? The cost of misclassifying a human as a gorilla is much, much, much higher than misclassifying a cat as a dog or an apple as an orange. Okay? So rather than fix the loss function or the loss matrix, we should be uncertain about the loss matrix. So when you begin working on some application, you should say, okay, I have some guesses about what the loss matrix might be, but I'm not sure. And the learning algorithm should operate with the uncertainty about the loss matrix, which means that then you have to put a prior distribution, probability distribution, over loss matrices, which is an interesting topic in itself, a new research topic. And also, your algorithm should be free to not classify some examples, because it says, oh, it's too dangerous to classify that one. I don't know enough about, what the risks are in classifying that particular image. Okay, so there's lots more I could tell you about the mathematical foundation of doing AI with uncertain objectives, but I also want to point out some of the difficulties. So the main difficulty is humans. All right, the math is all fine. The humans are the problem, because humans are not rational, right? We may not even have consistent, stable preferences. We are evil, right? And there's a particular kind of evil, which is that some of us derive happiness from the unhappiness of others, right? Now, if we try to satisfy the preferences of that human, then we're actually failing to satisfy the preferences of other humans by definition. So those preferences are in direct conflict with each other, and that's an interesting issue. Obviously, humans have different preferences. That's fine, right? We're not learning one set of human values. The robot is not adopting human values, right? The robot is just learning to predict what each of us wants our life to be like, and then trying to make that happen for all of us, Okay, so that's the basic idea. Now, there are some reasons why this problem is going to get solved, I think. One is that we have access to a huge amount of data, namely everything the human race has ever written. It's all about people doing things and other people being upset. Okay, so there's a huge amount of data we can learn from. And there's also a very strong economic incentive to solve this problem. We don't have to wait for a superhuman AI to come before we solve this, because systems that interact with us on a daily basis need to understand our preferences. And if they don't, then you can have some problems. So here's a situation where the robot is home looking after the kids, and you're at work late, as always, running your startup company, and the robot has to feed the kids, and there's nothing in the fridge. So what does the robot do? Maybe the robot doesn't have a credit card, but it sees the cat. À ce moment, then something bad happens. So poor Minou gets cooked for dinner. Right now, how many times would this happen before people stopped buying domestic robots? Right, once. This only has to happen once for people to say, I do not want that kind of robot in my house, right? And so there is a very strong economic reason why we have to solve this problem. We have to make AI systems that can deal with uncertainty about objectives, that can learn about human preferences by interacting with humans and observing humans. This is an essential part of making AI in the real world. So to summarize, I think everyone understands that AI is making rapid progress, and I believe it's prudent to assume that it will eventually overtake human capabilities. And that presents a risk to humanity, but I believe if we actually change the definition of the field in this way, we can make AI systems that are provably beneficial to us. And eventually, this will just be what we mean. This will be what we mean by AI, right? Just like the word bridge automatically means a bridge that doesn't fall down, right? You don't go around saying, I build bridges that don't fall down. You say, I build bridges, right? And when you say, I build AI systems, they should be provably beneficial. Just that's part of the definition of what we mean. Thank you.
Thanks a lot, Stuart. Thank you very much.